Hello, welcome back. Today we're going to be covering how to conduct a one-way analysis of variance or one-way ANOVA using Jamovi. In this video, we're going to cover what a one-way ANOVA is. We're going to cover how to conduct it in Jamovi, how to test the assumptions and determine if they are met and how to interpret those, and then also how to determine if we need to conduct post-hoc tests, and if we do, how to do those in Jamovi. We're going to be working with a research question today using the data set that is linked below. So I highly encourage you to download that, get it into Jamovi, and work along with me throughout this tutorial so that you can even better understand what you're doing and how to do it. Our research question today is, does the monthly dosage significantly affect the number of monthly symptoms reported by the patients? Let's dive into it. First up, let's establish what a one-way analysis of variance or one-way ANOVA is. So in the previous tutorials, we have covered t-tests. T-tests involve the comparisons of two means, and t-tests can only handle two means or two groups that we're comparing with one another. Now, where ANOVA comes and builds on that is that ANOVAs can handle more than just two groups. So instead of comparing just pre-test, post-test, or this group with that group, treatment control, an ANOVA can handle 3, 4, 5, even more groups that we're comparing. So it gives us a lot of additional flexibility in the kinds of research questions that we can ask when we're using an ANOVA to analyze our data. Let's say for today, we're going to be testing a new medication, and we're going to have some patients who are going to get a low dose of the medication. Some patients are going to get a medium dose of the medication, and then some patients are going to get a high dose of the medication. So those are our three different groups of our independent variable medication dosage. Our dependent variable or our outcome is going to be the number of side effects that the patients are reporting. So we can use an ANOVA here instead of a t-test because we have that low, medium, and high group, and that's 3 instead of just 2 groups. The thing about an ANOVA that is also an important difference from the t-test is that if an ANOVA comes back statistically significant, saying, hey, some of these groups are different from each other, great, but because there's more than just 2 groups, we don't know yet where those differences are. And that's where post-hoc testing is important and comes in, and we'll talk more about that in the analysis and interpretation coming up. So just like with t-tests, ANOVAs come with a set of assumptions that need to be met in order to determine if we can really trust the results of the analysis. There are 3 assumptions, and they should all be familiar to you if you have also watched any of the t-test videos. So first up, we have the assumption of independence, which states that all of the data points are independent from one another. This is a very important assumption. However, it is one that we typically take care of in the research design and data collection phase, not as much whenever we have the data and we're working in Jamovi. So what we're going to be testing within Jamovi is the assumption of normality. This tells us that the data are normally distributed in the population, specifically the dependent variable is normally distributed in the population. And then secondly, we have our assumption of homogeneity of variance. This assumption states that the variance of the different groups are roughly similar. So before we can get started with interpreting the results of the ANOVA, we need to make sure that we have met those assumptions, sort of like a baseline before we can move forward with the rest of our interpretation. So to show you how to do that and how to get into the interpretation, go ahead and have your data set open in Jamovi and we can get started. So you are going to click under the analysis tab onto ANOVA, and you're going to see that there is an option for you to select one-way ANOVA, but I actually don't want you to select that option. Instead, I'm going to have you select ANOVA. And this is because you could run this analysis in the one-way ANOVA tab specifically. However, the other types of ANOVAs that we're going to be covering after today are going to be conducted mostly in this ANOVA tab here. And it helps to be able to go ahead and get used to this tab. And also, and most importantly, this tab gives us a lot more options of things to click and other data that we might want to ask Jamovi for. So for those reasons, I think it's a lot more helpful. So you're going to click ANOVA and then ANOVA again. And then you're going to go ahead and move the reported monthly hours of side effects to the dependent variable box. And then medication dosage, that's our independent variable. You're going to move that to the fixed factors box. Now let's move on to testing our assumptions. So you're going to select under assumptions, the homogeneity of variance test as well as the test of normality. The homogeneity of variance test is also sometimes referred to as Levene's test. And so here, what we want to do is we want to take a look at the p-value. The p-value is going to tell us whether or not we have violated this assumption. And the rule is that when testing assumptions, we want our p-value to be greater than 0.05. In other words, we do not want a statistically significant p-value when we're testing our assumptions, because what that indicates is that our data are statistically significantly different from what would be ideal. So if we were to find a statistically significant p-value for the test of homogeneity and variance, that would tell us that the variances of the different groups are indeed not similar, which is not a good thing. We want them to be similar. So if the p-value is greater than 0.05, assumption is met. If the p-value is less than 0.05, then we might need to make some adjustments in our analysis. So in this case here, our p-value is 0.436, well above 0.05, so we're good to go. We have met the assumption of homogeneity of variance. Now let's take a look at the second assumption here, the test of normality, also called the Shapiro-Wilk test. So same rules apply here. We are looking for a p-value greater than 0.05. And here in this situation, our p-value is less than 0.05, indicating that we have indeed violated normality. But I want us to pause before we panic. If you were out in the real world and this happened to you, here is what I would recommend. So the first thing that I want you to keep in mind is that ANOVAs, like t-tests, are robust to violations of normality, which means that if we violate normality, these tests can sort of take a hit, so to speak. They can handle a little bit of variations away from normality, especially if sample size is sufficient. The rule of thumb, according to the central limit theorem, is that sample sizes above 30 are considered sufficient when we have potentially violated normality. So here, our sample size is 150. So we are well above that threshold of 30. So we think, okay, we have a decent sample size, we have violated normality, but we probably are okay because of that sample size and the fact that ANOVAs are robust to violations of normality. But I would always recommend going ahead and getting a better idea of what's happening with your data. So what you can do here is you can actually, under where we selected the test for normality, you can also go ahead and ask for a QQ plot. This is available in t-tests as well, but we haven't talked about it as much in previous videos. But this is a way for us to visually inspect the normality of our data. And what we want to be looking for is that the dots along the plot should fit pretty well to that trend line. If they are far away from the trend line, that is indicating that they are veering from normality. And you can see here that we have some veering happening, particularly in the tails. So that tells me, okay, there's potentially some skewness happening with our data. If you wanted to get an even better picture of this, you could go to exploration and descriptives, move the dependent variable over, and then ask Jamovi for a histogram. And you could again see, okay, when I'm looking at the plot of our data, it doesn't look too terribly far away from normal, but there is probably some skew happening there in the tails. Now, because, again, ANOVAs are robust to violations of normality, and because we have a sufficient sample size, I am not overly concerned about this violation. If I were writing up these results, I would note it. It's important to be transparent when you're writing your results. I would say that there was a violation, talk about the QQ plot, talk about the histogram, all of those things. Let's say, though, you, for whatever reason, need to be extra careful and conservative. You can always run a non-parametric version of the ANOVA. We aren't going to really talk as much about non-parametric ANOVA in this particular video, but I mentioned this in other videos as well. If you want more information on non-parametric testing, let me know, reach out, or leave it in a comment, and I'm happy to make a video covering that. So that's our assumptions. Now we can ask Jamovi for a couple more pieces of information to start interpreting the main ANOVA analysis. So I want you to scroll back up a bit, and I'm also going to have you select an effect size from Jamovi. I want you to select the box for partial eta squared. That's how we're going to be measuring our effect size. And that should give us some results that we can start to take a look at. So two main things to focus on here. First, the p-value. If p is less than 0.05, then that means that the medication dosage significantly affects the reported effect sizes. If p is greater than 0.05, then that would mean that there was no significant difference in the group. Here we have a statistically significant p-value, and that tells us, hey, yeah, there are some statistically significant differences across the different groups for the reported side effects. So neat, we found that. Before we interpret that further, I also want to take a look at the effect size and talk about that interpretation. So previously, when we covered t-tests, the effect size we were working with was something called Cohen's d effect size, or a standardized mean difference effect size. Here in ANOVA, for the primary ANOVA analysis, we're using something called a partial eta squared, and you can interpret this as variance explained. So this tells us how much of the variance in the side effects is explained by the medication dosage. So in our case, we have a partial eta squared of around 0.4. 0.426. So that means if you scooch over the decimal point, that 42.6 of the variation in side effects is due to the dosage. So that's close to 50%, almost half of the variance in the side effects can be explained by dosage. So we would consider that a large effect size. So we've got a statistically significant difference and a large effect size. But I want to pause for a minute and remember that we said when you have more than just two groups in an ANOVA, if you find statistical significance, you know that somewhere between those groups there's a difference, but we don't know where yet. Or another way to put that is we haven't yet localized the effect. So in order to localize the effect and figure out which groups are significantly different from the other groups, we have to conduct something called post hoc testing. So that is another way of saying additional tests after the main analysis. So we have three groups. Again, we have the low dose, the medium dose, and the high dosage groups. So we need to conduct a post hoc test to find out which groups are different. So you can go to post hoc tests, move medication dosage over, and you need to choose a correction factor, because since we are running multiple analyses, we run the risk of inflating our type 1 error rate or our rate of getting false positives. So all of the different options here are ways that you can apply a correction factor to those additional analyses to control that type 1 error rate. There are slight differences between them. Some people prefer some over others. I prefer the Bonferroni correction because it is also very easy to conduct that correction factor by hand. And so when you don't always have Jamovi with you, you can still use the Bonferroni correction factor because you just take the number of tests that you are conducting and divide that by 0.05 or your alpha level. So that's a little bit beyond the scope of the purpose of this particular video. I'm going to choose the Bonferroni correction. If your preference is Tukey or Shapiro or something else, you can feel free to select that instead. The interpretation will be the same. So Bonferroni correction is simple and widely used. I'm going to click that for this, and then we can take a look at the output. So we're going to get now what these are called our pairwise comparisons. They're essentially t-tests. Now, instead of having the overall ANOVA, which is comparing all three groups, now we're doing pairwise comparisons. We're comparing the high group with the low group, the high group with the medium group, and the medium group with the low group. And we've got some data here in this table that we can take a look at. So this is going to give us the mean difference between the groups, which is helpful. And then importantly, it's also going to give us the p-value for the groups, and we can see that all three groups are statistically significantly different from one another. And you can see here that this shows that this p-value is being corrected by the Bonferroni correction. And again, that's beyond the scope of this video, but just know that that correction factor has been applied here. So all three groups are statistically significantly different from one another. That's what post hoc testing is important. That's the information that we can get from it that we can't get from the main ANOVA. We could have gone and conducted post hoc testing and found that only the high group and the low group were different. But here we found that all three groups were statistically significantly different from one another. This output table also gives us the value of t, because remember, these are t-tests. And we asked for the Cohen's d effect size as well. If you didn't click on that, because I think I might not have mentioned it, you can go back into the post hoc testing tab and ask for Cohen's d effect size and the confidence interval for that effect size. But that way you can also understand not only the p-value of the comparisons between these groups, but then how large of an effect that is. And you can see again with all three that the effect size is large. A Cohen's d is considered large at values of 0.8 and higher. So all of these are not only statistically significantly different from one another, but the effect size of that difference is large. Now, another thing that can be helpful as well is to be able to actually visualize the plots here to take a look at what those differences look like. So you can go to estimated marginal means and again, move over medication dosage. And I like to select both the plots and the tables. The plots give you a visual representation, but the tables list the means of each of the groups, and that can be helpful information as well. So here we can see with our plot that as the medication dosage goes up, the side effects reported go up as well. So they are side effect reports are lowest for the low medication group and highest for the high medication group, moderate for the medium medication group. So we can further see what's happening with our data. This can help us wrap our heads around it a little bit more clearly sometimes if p-value and effect size are still feeling a little bit just not as concrete for us. Sometimes being able to look at it on a plot and visualize it can help even more with understanding and trying to interpret the results of our data. So you've done it. You've successfully conducted a one-way ANOVA in Jamovi. We talked about what a one-way ANOVA is, how it's different from a t-test. We talked about how to test the assumptions of a one-way ANOVA, what to do potentially if you violate normality. We talked about how to conduct the one-way ANOVA and post-hoc testing all within Jamovi. So of course, if you have any questions, I'm happy to answer them. You can reach out to me in the comments below or through my website at ajoytoteach.com. And I'm happy to chat with you further. In the next video, we're going to be covering two-way ANOVA, which is going to get even more interesting. So I hope to see you all then. Bye.